The next part of Chapter 7 will really test how well you can work with fractions. And we are going to work with fractions in very abstract ways. So in grades 7 and 8, you added and subtracted fractions with numbers. Then in grades 9, 10, 11, you started using fractions and with variables. And in grade 12, we're going to use variables and sign functions to work with fractions. So we revisit our fraction rules. And first of all, some strategies for simplifying fractions. The main strategy is, can you write a bunch of fractions as a single fraction? That'll always be a strategy for simplifying fractions. So when we look at these four examples, and we're going to do them in this order, actually only number 3 is a single fraction. Number 1 is adding 2 fractions. Number 2 is dividing 2 fractions. And number 4 has fractions inside of fractions, adding and dividing. So a key strategy for simplifying fractions is, do you know your fraction rules to write things as a single fraction? In other words, do you know your fraction rules for adding and subtracting, multiplying and dividing? Secondly, sometimes when you have a single fraction, it's not simplified because you would be able to factor, and there's a common factor. So for example, if someone told you 5 out of 10, well, you could reduce that to 1 out of 2. And 1 out of 2 would be considered simplified. 5 out of 10 isn't simplified yet, because there's a common factor of 5. You can divide both of them up. So that's with numbers. We're going to do the same thing with algebra. So let's practice our fraction rules. Do we remember, number 1, how to add fractions? The rule for adding fractions is you need a common denominator, and then you can add the numerators together. So do we have a common denominator? No. So what would we need? We would need a C on this one and a B on this one. And if I multiply the top and bottom, I change what the fraction looks like, but not what it's equal to. Does it make sense that C over C is equal to 1? So I'm multiplying by 1. When you multiply by 1, you don't change what something's equal to, you just change how it looks. And we need to change how it looks so that we have here AC over BC plus here B squared over BC. We needed to change what it looked to get our denominators the same. Because the rule for adding fractions is you can only add fractions if your denominators are the same. And then if they are the same, you just have to add the tops. So we have taken 2 fractions and now written it as a single fraction. This is considered simplified. When you get to variables, it doesn't look more simple than what you started with, but apparently it's simplified. So getting a single fraction is simplified. For number 2, we have A divided by B divided by C divided by D. So we have to remember, what is your fraction rule for a fraction divided by a fraction? Fraction divided by a fraction, keep the first one the same, and multiply by the reciprocal, or flip the second one and multiply. How do you multiply fractions? You multiply your numerators, you multiply your denominators, so in the end, this one will be AB over BC. And we have succeeded in getting a single fraction. Number 3 is already a single fraction because we have a squared minus ab over b squared minus a squared. So if you already have a single fraction and it's not simplified, it might mean there's a common factor. So what do we have to do? We have to factor the top. In the top, I notice that there's an a in common, and I can factor that out. In the bottom, I have a difference of squares. So I have b plus a, b minus a. And in order for something to cancel out in fractions, one, you have to be multiplying. That's why we factor. Some people will be tempted to cancel out these a squareds here. Never allowed when you're adding and subtracting. When you're adding and subtracting, that groups something together as single factors. So this is a single factor divided by this is a single factor. And the only way something cancels out or simplifies is if there's something identical. So this whole thing grouped together is not identical with the whole thing grouped together at the top. Even after we factored it, nothing is identical yet. I have an a minus b, that is not identical with b minus a. They're close, but they're not identical. And this is a note your grade 10 teacher probably wrote down, your grade 11 teacher probably wrote down. I'll write it down again for grade 12. Whenever you have something like b minus a, you can factor out a negative, and then it would become a minus b. Taking the negative out of the b makes it negative. Taking the negative out of negative a would make it positive. That would allow me to rewrite this with a negative there. And you can write it just as a negative or a negative 1. And now I have factors that are identical, and they will simplify. Which will leave me with, and if you have a negative in the fraction, you can put it either on the top, on the bottom, or in front. I put it on the top here, because if I left it on the bottom, I'd have to leave brackets around the b plus a, which is the same as a plus b. And now this is simplified. And for number 4, and number 4 probably shows up the most in this unit, we have a over c plus 1 over b all divided by b plus c over a. So we're going to sort of use the strategies that we had before, but I'm going to describe it out a little bit more. First, we're going to get a single fraction in both the numerator and denominator. Then we're going to divide. So because we have fractions inside of fractions, you have a rule for a fraction divided by a fraction, but that rule is only when you have a fraction, one fraction on the top, divided by a fraction, one fraction on the bottom. We have two fractions on the top, and technically, if I make that over 1, two fractions on the bottom. So in order to do a fraction divided by a fraction, your dividing rules, you need a single fraction in your numerator and a single fraction in your denominator. So to start off with, that's what we do first. I'm going to get one fraction in my numerator. In order to do that, I need a common denominator. This needs to be multiplied by b and b, this by c and c. Same thing in my denominator. To get a single fraction, I'd have to add these together. This one needs to be multiplied by a and a in order to get a common denominator there. One thing I like to do with these questions that have lots of fractions, I like to make my main fraction line sometimes thicker, sometimes longer. Can you see in your numerator of your main fraction, you would now have a common denominator BC, and adding the tops, you would have AB plus C. In your denominator, you would have a common denominator of A, and you would have AB plus C. And now that we got a single fraction in both our numerator and our denominator, now we can use our fraction rules for dividing. Fraction divided by a fraction. Keep the top one the same. Multiply by the reciprocal of the bottom one. Now we're multiplying. This would get grouped together because of the adding as a single factor. This would get grouped together because we're multiplying and we're adding there. That would be a single factor. If I have factors that are identical, which I do, they can simplify. Those would become just ones. And now when I multiply the tops, I get A on the top and just BC on the bottom. We are going to use these strategies a lot in this unit, but instead of using variables, instead of A's, B's, and C's, we're always going to have trig functions like sine theta, cos theta, tan theta. So you're going to have to practice your trig rules with those. Okay, so turn to page 606. And first thing we're going to do is we're going to take out our highlighter and highlight the definition of a trig identity. A trig identity is a statement that's always true for all angles. So if something's always true, we call it a trig identity. We have already learned a couple of trig identities, and they're listed here. You learned that cosecant was the reciprocal of sine. So cosecant is 1 over sine, secant is 1 over cos, and cotangent is 1 over tan. With these, I'd like you to also write down that as a result, sine theta is 1 over cosecant theta, cos theta is 1 over secant theta, and tan theta is 1 over cotangent theta. We also had one of our big ideas in chapter 6, that tan of theta is always sine of theta divided by cos of theta. And as a result, cotangent theta is always cos of theta divided by sine theta. And we're going to add another big idea that we had from chapter 6. We know that sine squared theta plus cos squared theta is always 1. So as a result of this, the next thing that we're going to be working on over the next week after your test is proving identities. So we're going to start off with this sheet and working on it together. You'll need to take out some loose leaf. If you don't have loose leaf, I have some extra. Loose leaf. Yeah. All right, so what we have on the paper is, and we're doing the side that has identities written all around it. We're going to start and do number 5 together. We are going to try to prove that cos of t times secant of t is equal to 1. Now there's some rules and regulations with proofs. Rule number 1 is that you are trying to prove this is true, so you can't use you are not allowed to move things from one side of the equation to the other, because the only time that you can move something from one side of the equation to another is if it is true, and you're trying to prove that it's true. So one of the mistakes that some people make in a mathematical proof is they use what they're trying to prove is true to prove it's true, which causes problems. So the way that we prevent that problem is step number 1. After we rewrite what we want to prove, we draw a line down from the equal sign to make sure that we only work solely on the left side by itself and the right side by itself. We never move something over that line. So that's step number 1 in a proof. Step number 2 in a proof is you are allowed to use anything from this that you like. So if you see a cosecant, you could decide to rewrite it as 1 over sine. And our job, or what we want to do, is we want to make the left side and the right side identical. So a starting point on this one is I have a cos t and I have a secant t. When I look here, I could either change the cos t to 1 over secant, or I could change the secant to 1 over cos, or I could change them both. And one of the things that students find sometimes difficult in a proof is, what should I change? Okay? In this case, I would say, well, you're probably more comfortable with sine, cos, and tan than you are with cosecant, secant, and cotangent. So let's start by changing secant to 1 over cos. And now I introduce fractions, and I have to do my fraction work, which says, can you write this as a single fraction? And if you have a fraction times a fraction, you multiply the tops, multiply the bottoms. If you have factors that are identical, which these are, those cos t's would simplify and just become 1. And then you have 1 times 1 on the top and 1 times 1 on the bottom. Pretty obvious that the answer is 1 on this side. And if you're able to simplify the two sides, now the left side and the right side are identical, you are done. All we have to do is write a statement that says we noticed that the left side was equal to the right side. So in the statement you write 3 dots. 3 dots is short for therefore. Therefore, the left side equals the right side. And then in mathematical proofs, often you'll see in textbooks or online, if someone's done a mathematical proof, it ends with QED. It's a Latin abbreviation. It's like, yeah, I know my Latin really well. Okay, it's sort of historic that they write QED at the end of the proof. My Latin is probably terrible, but none of you probably know Latin. So the Q stands for quod erat demonstratum, which translated to English says, what you asked for has been demonstrated. And so you asked me to prove this, I did that. Now, for me personally, something I've always done since university, I draw a little box and add some shading at the end of my proof. It's sort of like I feel really good about proving this. You can add your own symbol, like if you like a happy face, and you don't have to do anything, but you'll always see me add a little symbol at the end of my proofs. It's just something that I do. So, what we need to do is we need to use what we have here, change things until we get the left side equal the right side. Write a statement saying the left side equals right side. Then you can add some fancy stuff if you like, the QED. So we're going to do a couple of these together. We're also going to do number 9. So number 9, we have cos of y, cosecant of y equals cotangent of y. And in number 9, I am going to introduce to you a proof strategy that works really well most of the time. And that proof strategy is making an observation that no matter which of the 6 trig functions you have, you can always change them to either having sine or cos or both. Let's look at all 6. If you have cosecant, you could change it to 1 over sine. If you have secant, you could change it to 1 over cos. If you have cotangent, you have a choice to either change it to 1 over tan or to change it to cos over sine. I will tell you that more often you will change it to cos over sine. And same thing with tangent, you can change it to sine over cos. So because you have so many options of things to change things to, a good strategy is saying, well, first, let's change everything to either sine or cosine or both and see what happens. Because it at least reduces things to only 2 trig functions. So in this question, I would keep cos the same. No need to change it because it already has cos. But I would take cosecant and change it to 1 over sine. I would take cotangent on the right-hand side, and I have 2 options, but I would choose to change it to cos over sine. Now, can I get a single fraction on both sides? The right-hand side is already a single fraction. The left-hand side is a fraction times a fraction. How do you multiply fractions? Multiply the tops, multiply the bottoms, and if I do that, my left side and my right side are the same. So I can write my statement, my left side equals my right side. And finish my proof. So the idea of changing things to sine and cos often then leads you nicely into making both sides identical. We'll do one more together. Let's do number 13. So again, even though there are lots of things that you can change, as a first step, I would decide I'm only going to change things to make them sine or cos. If I have a sine or cos, I'm going to keep them the same. So if I think that way, the only thing that's different than sine or cos is tangent, and I can change tangent to sine over cos. And I now have a fraction inside of a fraction. So our strategy of fraction inside of a fraction, can we make the top a single fraction? It is already. If I change the bottom to sine u over 1, it's a single fraction. What's your rules for a fraction divided by a fraction? We multiply by the reciprocal. So I flip the 1 over sine u. And then I notice, since I'm multiplying, I have 2 factors that are identical. They can simplify. which leaves me with 1 over cos u. And I look at the other side, and that's what I wanted. So now I can write my statement. And be done. Got a little fancy. Okay, so over the next week, we are going to be developing more and more strategies because they start off easy, and along this page, they get harder and harder. Right now, I would say you're probably good up until 20. Okay? Anything past that, then the strategies start getting harder, and we'll have to develop some more stuff. But for now, the rest of class, we are going to work on proving as many of these as possible.